the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 60, where today we are going to be talking about the elegance of trigonometry. So interestingly enough, this is the very first time that we announced a future episode in a previous episode. So if you guys heard the last episode, it was a comment of the week that actually made us, was like, hey, why don't you guys do trigonometry? And
that was actually by accident, by the way.
Here we are.
Because I picked the comment like right before we started recording, and I didn't realize that was gonna give up the topic of this week.
You didn't know that?
I didn't plan that ahead, but I mean, I guess it just happened.
You didn't even know. Well,
the point is, here we are. We are. It was a great idea, and now we're making an episode on trigonometry.
Yep.
If you do have, recommendations for topics, something you want to hear us talk about, make sure to leave it in the comments, or just leave a random comment, and you might get selected as the comment of the week on next week's episode.
The comment of the week for this week's episode, though, is a nice one. I don't know who it is. It is some interesting username, DJDJ12. I don't know if that means something. And he commented, or she commented, "Love the podcast. This is one of the reasons I want to pursue physics." Wow.
That's great.
Thank you,
That's amazing.
DJDJ12.
Physics is probably the greatest thing you could ever study. So, we encourage everybody to do some math, do some physics. They do go hand in hand. And then maybe you'll realize like, hey, physics is more than just projectile motion and force diagrams. It gets pretty interesting when you start learning things like quantum mechanics, for example.
Yeah, of course.
Something that a lot of people find super mysterious, but it's based off of observational deductions and things like that, and it's a pretty bulletproof theory. It hasn't been like
Wait, you're talking about quantum theory? It's not really. I mean, it's bulletproof in whatever. Like we only have a very select range of bullets, and yeah, it blocks those bullets, but we don't know the number of potential bullets.
What are you talking about?
What I'm trying to say is, quantum theory is still like disputed in a lot of like nooks and crannies. Like the essence of it.
No, but I'm saying that every experiment that we do is aligned with quantum.
All the experiments
theory,
again, we know how to do. That's what I was saying. The bullets, like all the bullets that we have.
Exactly.
So all the
So
experiments that
far,
we know how to do so far all make sense with quantum theory. So yeah, but the thing is, we probably only tested out like this small 2-3%, maybe even less of experiments that there possibly are. Who knows?
Oh yeah. By the way, I wanted to let people know, like people who send us emails, we see your emails. We just get lazy to reply to them. But just know we do see all of your emails and we read them, and we will reply to them eventually. We just try as much as we can.
Because a lot of the times, like we read the email and we're gonna reply to them, but again, because of this, laziness, like you've so well put it, we just say, oh, we'll do it later, we'll do it tomorrow, and then we just keep forgetting. So like, don't worry, we have read it. True. Like we will get to you. It's just that sometimes we just forget. Yeah.
In other news, 8,000 followers yesterday.
Oh yeah, that was
great.
Amazing.
That was fantastic. And by yesterday I mean Friday.
True.
Not because this goes up on Monday. Yeah. But yeah. We're almost at 10,000, which is going to be crazy, of course. And this is just on Spotify, by the way. We do have like 500 subscribers on YouTube. We have like 400 followers on another platform. I have no idea how many followers we
Google.
have on Apple because they don't tell us.
Our Google
like
podcast
that.
numbers have increased. We used to have like 4%
That's
of our listeners, I remember, on Google Podcast. Now we have close to like 7.5. Not a big difference, but it's still a difference. So like
Cool,
I'm just saying,
cool.
cheers to those Google
All right.
Podcast listeners. And we also topped 110,000 downloads this week. So we're at 112,000 actually right now. So yeah, we're gunning for that 200,
That's
and then
crazy.
hopefully for the 500.
No, we're gunning for the million.
Well, we're
right
gunning
away.
for the
We're
million,
going-
obviously, but like
We're going
short-term
straight for
goals
the
first.
million.
Short-term goals first, for sure.
So
Anything else? Any
yes,
other news we need to bring up?
I don't think so.
I don't think so.
Let's start talking about trigonometry.
Trigonometry.
Wait, wasn't there something else? Oh yeah, the live stream.
Oh my God, we forgot about that. Yes, the
Sorry.
100K Q&A, ladies and gentlemen. The 100K Q&A will be taking place live on YouTube Saturday, 15th of May at 12 p.m. Eastern Standard Time. So we will be announcing this on Instagram, like on Friday, on Thursday. Like we're going to be posting it on our stories, reminding everyone, all that kind of stuff. But we're also going to be having a post. So if you guys do follow us on Instagram, just forget the date. Don't worry, you can see it there.
So
yeah.
make sure to follow us on Instagram
Exactly.
at math.physics.podcast. We're almost at 1,000 followers on Instagram, which is cool.
Oh, yeah.
So make sure to check us out there.
Yeah. Awesome.
Okay, so let's get into trigonometry and talk about triangles really quickly.
Let's get into it. Yeah, the first base, I think, with trigonometry. Parker and I were talking about this before we started. We were like, is it circles or is it triangles? And at least the first time I learned trigonometry, and I think most people learn trigonometry this way in high school and stuff, with the idea of a right angle triangle, right? So trigonometry always works only with these right angle triangles, and the interesting thing
Hold on, that's not true.
it's
No.
okay, it's defined using right angle triangles. Sorry, it doesn't, obviously it can work anywhere. It's defined using right angle triangles.
I guess
Like sine, theta, by definition, requires a right angle triangle. It requires a 90 degree somewhere in that angle.
I think it's more of like a coincidence, but
You think so? I don't know.
Yeah, because you're not drawing a right angle triangle on purpose. You're just looking at the x coordinate.
That's what I'm saying. I think it's because of the fact that you're talking about the x and y basis vectors. Like you're talking about the fact that you're moving in one direction and the other direction is orthogonal to it. So I think simply because of the nature of the Cartesian
I'm not following
plane,
what you just said.
So are you saying that because of the nature of the Cartesian plane, we have 90 degree triangles? That's what you're saying.
No,
basically.
I'm just okay. We're gonna talk about this later.
Okay, yeah, we dive too deep into it in the beginning.
The first thing that has to be stated is that trigonometry sounds like it's about triangles, but in fact, it is about circles. Why is it about circles? Well, the circle is like the most perfect shape that exists in nature. And I guess one way you can think about a circle is that if you want to draw a shape, you can look at the vertices, right? And if you have two vertices, you can't draw a shape, you just have a line. And then as soon as you add a third vertex, you can draw a triangle, and then you can add another one. And then you have things called like regular polygons. Why did I say it like that? Regular polygons, where each side and each angle has the same length and same degree, right? And those are like your squares, regular pentagons, things like that. And then what you do is you just crank up the number of vertices to infinity, and you will have a circle. So you can either think of the circle as an infinite-sided regular polygon, or you can think about it as a one-sided, like, just, it just has one side.
Yeah,
no
because,
angles.
technically it doesn't have any sides. Like a circle by definition, like doesn't have any corners either, right? So by definition, that's the beauty of a circle, right? And I believe and we are going to be talking about, the idea behind pi as well. And because you were bringing it up this way, I think it's kind of nice to talk about in a number file video, I believe. And I think, was this how pi was thought about, or was this simply like a consequence that they found where they were trying to find the area? So basically they were approximating the area of a circle with radius 1. So they were approximating that via using these polygons and increasing the number of sides to infinity.
That's not how it was done.
That so? That was not how it was made, but I believe
No.
that it's a consequence that basically that tends to pi.
So I think how like initially pi was found because they realized that like the ratio, like the radius and the circumference is proportional for any circle, right? It's equal to some constant. And then, they realized soon after that constant is not rational, and so you have to approximate it by some number. And then they started approximating it using like regular polygon approximations.
Mm-hmm. So
Yeah.
the very first official okay, well, technically I'm reading here like the ancient Babylonians also, approximated pi as equal to 3 by taking, just the radius of a circle. I'm assuming a very simple approximation, but the first mathematical calculation that we have of pi was by Archimedes himself, when he took a circle and he's like, okay, I'm going to inscribe a polygon inside, and I'm going to inscribe a polygon outside.
We have talked about this before.
Yeah, I think we have.
when,
and this is a beautiful consequence. And I think I still remember there's some video or some article that I've read where they talk about the futility of this method with what we have today to calculate pi. Because this method is basically done by calculating these areas of these polygons inscribed inside and outside. So basically you get a lower bound and an upper bound for pi. So the more sides and the more of these, basically the more sides you have, the closer you get to the circle, so the more you approximate. And up until don't quote me here, but up until pretty recently, before a new method of pi was found, people were literally spending their entire lives. I believe there was one mathematician spending like 30 years solving like 20 digits of pi.
Yeah.
And now we can do that with
you know what actually happened in the past, what they would do is they would manually, like, they would use that method to approximate pi, but they would have to calculate it by hand. And then comes Newton, okay? Newton was actually fascinated by the Binomial Theorem, which is basically you have two terms and then raised to some power, right? And what he actually did, this is actually very intelligent,
this guy
right?
is a genius, man.
He used calculus, which he came up with, and so we know that the equation for the top half of a circle, right? You can say it's like y is equal to, and let's say it's just the unit circle, so it'll be the square root of x squared, or square root of 1 minus x squared. And so what he did is he took, he went from 0 to 1, right? So that he got the top right quarter of the circle, and he took the square root of 1 minus x squared as a binom, right? So you have 1 and then minus x squared, and then all to the power of 1/2. And what he did is he expanded that using binomial theorem, and then of course you have like an infinite amount of terms. And so what he did is he cut off at a certain point the amount of terms, and then integrated that from 0 to 1. And it's actually a very easy computation, right? Because it's essentially you're left with integrating a polynomial, and your bounds are 0 and 1. So all you're going to be left with are the coefficients of your, like, each term in the polynomial. And so he was actually able to, like, when you calculate the area of a circle, but only the top quarter, and this is the unit circle, then you're calculating pi over 4. So to actually get a value, an approximate value for pi, he just multiplied that integral by 4, and he actually got very close. I think it was the equivalent to hand calculating the area of like a polygon with 300,000
Yeah,
sides.
I remember something like
That's
that.
how that's how precise his method was. And it literally, that calculation is so simple.
And he cut off
It
so many
took
terms
him-
too, you know?
Yeah, he cut off so many terms and it was so accurate. It was mind blowing. When I read about that, I was like, man, this guy is
Newton
on
is
a
on a
different
new level because this
On
guy
a
didn't because
different level.
if you think about it, like Archimedes is like 200 BC. Newton is like 1600s. So that means
Yeah.
for like 1500 plus years, like 16
Yeah.
1700 years, they were trying to calculate pi using these approximations, using these polygons in such an infutile way, because at the end of the day, like after like all the way up until like 1500 or something before Newton, I believe the most digit they had got was like 20 or something, which was like,
But imagine for like 1,000 or like thousands of years, people have been like walking in between like cities, and it would take them days
Yeah.
and months to walk between cities. And then Newton comes around in like a sports car and just like out of nowhere drives like, and it takes him 2 seconds. Everyone's like, "Bro, how did nobody think of this?" Well, you know, Newton invented
Yeah.
the tools that he used
exactly.
to like.
I was
he,
just gonna
he
say.
built the car. He did it all himself,
Mhm.
and you
He
know,
literally
it
wrote the
worked
tools
out.
to solve the question. Like, it's not
Yeah.
like he used something else. So it's not really that it was
Yeah.
that obvious to other people, right? Because everyone
Mhm.
was completely astounded. And that's also why, you know, Newton was such a highly respected physicist. Because obviously, like, he invented his own form of mathematics to solve the world's problems, you know? And that's such an interesting way, like, that's such an interesting take on just calculus, you know?
Yeah, definitely. But anyways, enough talk of all of these things. We got to get back on track to trigonometry. So let's talk about degrees versus radians.
Oh, okay. This is
So
this is
it's actually
interesting because
interesting.
every grade 12 kid, or every person who like
Yeah.
gets into radians, or at least in my class I remember, just hated it, because you have to think,
Yep.
because your original 180 degrees, 360 degrees now turns into pi
Mhm.
and 2 pi, and it's so weird. But
It made so much sense to think in terms of degrees.
yeah,
But the thing is, like radians are so superior.
now
Is
we
it
think
so
about
much
things in terms of radians.
superior?
Like everything that I think about in terms of a circle is I don't think we've ever spoken about degrees in a very long
No,
time.
I don't. Actually, in astronomy, we actually talk about degrees.
Okay, astronomy is okay. That's a little.
but
I'm talking about like
everything
math,
everywhere
or at
else,
least
yeah.
yeah. I'm talking about like physics, math right now, especially like when we're talking about. We're gonna get into some cool things with angles and you know these radians and the use of these radians. So
Yeah. And the reason
Yeah.
why it's called radians,
Yeah.
it may remind you
Yeah.
of the word radius.
Uh-huh.
Okay. And for all those maybe who don't know, radius is a length from the center of the circle to the edge. And if you can visualize a circle in your head right now, you'll realize that the radius is the same no matter which point you pick on the edge. Okay, you start at the middle, you go to the edge, you have the radius. The reason why we have this way to calculate angles, and it's called radians, is essentially because you have this you have a circle, and instead of thinking in terms of degrees, which is essentially cutting your circle up into 360 little segments, and then you say, you know, this many segments, and you have this angle. And instead of doing that, you say, how many, like, if I walk along the circle, how many radii am I walking along? And as we mentioned earlier, the ratio from circumference to radius is actually 2 pi, which means if you walk 2 pi radii along your circle, you're going to come around to where you started.
Mhm.
And so that's how we describe angles. If you want to go a quarter circle, then you go pi over 2, because pi radians gets you halfway, pi over 2 gets you a quarter of the way. And so that's how you have to think about radians. You multiply by 2, and that's an entire
Well, I mean, before even thinking about the whole 2 pi situation, like you
revolution.
can just think about, well, 1 radian, even though we never really use it in terms of numbers. Like I've never really seen 5 radians. It's always some multiple of pi. But before we're like, even though you've already spoken about it, like the idea behind like 1 radian is so like if I want to walk the equivalent of 1 radius, like however big my radius is, like that would be equal to 1 radian. And I think that is the definition
so it's like
of the
that
radian.
angle. The angle that ends up being, that separates you from your position on the circle to where you started is defined by how many radians or radii you walked
exactly
along the circle. And the reason why this is great is because it's very neat. You know, if you think about degrees, you think, okay, you have 0, 90, 180, 270, 360. It doesn't really make so much sense. It's just because we're used to it.
To us right now, because we're used to it. Exactly.
Yeah, it's because we're used to talking about degrees. But when you get used to talking about radians, it's like it just makes so much sense. It's like you start using a hammer to hit nails instead of your hand.
But also it does depend in the context. It does heavily depend in the context. Like, for example, if you're doing any type of, engineering or construction, you're not talking about radians. You're probably talking about degrees. You're probably saying, okay, the stairs are inclined at 30 degrees or something like that. You're not really saying pi over 6 radians.
But one reason why radians are so useful is because pi comes up everywhere in mathematics. Literally everywhere. And so when you have a system to describe angles where pi is literally everywhere, you're talking about pi over 4, pi over 2, 2 pi. The way you describe your angles has everything to do with pi. And then pi comes up naturally everywhere in mathematics. It all blends together so well that you could do it in degrees, but there's no reason why you should.
And another thing about radians, a very interesting thing about radians is that it is the ratio, again, between how much you've traveled and that radius equal to basically how much you've traveled versus the radius of the circle. Now, what is an interesting thing about how much you've traveled and the radius of the circle is that they have the same units. So radians, by definition, is unitless. And this is actually very cool because, and we're going to get into like angular velocity, which is a really interesting idea and especially heavily used with radians. It's useful because radians are unitless. So when you say radians per second, which is like a unit for angular velocity, I know I'm getting into it and we haven't gotten into it.
Yeah.
But I know, but just hear me out here. Radian per second, which is like a unit for angular velocity, can be thought about as frequency, because
hertz.
Radian as hertz, because a radian is unitless, so you can just say as units it's just 1. So 1 over second by definition is hertz, which translates to frequency. So your angular speed is related to frequency, and I think that's an amazing that's an amazing relationship because the radian by definition is unitless.
And one realization that's always great when someone realizes this the first time is that you have a wave that oscillates up and down, and you realize that that wave is literally connected to a circle by its angular velocity, because you can think of the oscillations of a wave as an angle going around a circle, or sorry, not an angle. Well, this is connected to the sine and cosine, I guess we should talk about first and then come back to this topic. But yeah, before we actually get into like sine, cosine, and then trigonometric identities, I do want to make my case here for tau.
Oh my god.
Now
this again, man. Not this again. Let's hear
now hear me out, okay? To me, this makes so much sense, but Ray actually does have a counter argument, which I'm sure he will let you know. Essentially, tau is 2 pi, okay? So it's literally just pi multiplied by 2. So if you were to talk about a full revolution around a circle, you say it's tau radians. Okay, but why is 2 pi so significant here? Because I think when students learn about circumference and area, it will lead to like faster understanding of the two. But hear me out,
Let's hear
okay?
it.
So first of all, you learn about circumference, and you're told it's 2 pi r, r being the radius, which it kind of comes out of nowhere, right? You're expected to just memorize that formula and just deal with it, right? But it's actually cool when you learn calculus, like 5 years later, you actually like derive that formula, and you're like, oh, that's interesting. Anyways, then you learn about area, and it's pi r squared. That also kind of comes out of nowhere, and you're just expected to memorize it. But notice how the circumference is 2 pi r, and tau is 2 pi. So instead of telling students that circumference is 2 pi r, they think of it as tau r. Okay? So they associate tau with circumference and pi with area. Now, so when you think about circumference, tau r. When you think about area, pi r squared. Now, why does this make more intuitive sense, at least to me, is because you have a constant and then a variable. The constant in the term in circumference is going to be tau, and the variable is r, and r has units of meters, centimeters, whatever you want. Mm-hmm. But when you're thinking about area, you're thinking about a constant, pi, times r squared, which gives you units of meters squared, which is area, right? So all you have to remember is your units, right? And so if you're trained from a young age to think circumference, tau, area, pi, you get asked the circumference, you think, okay, so circumference is length, units of meters, it's just tau r, units of meters. You're asked area, you think pi, meters squared, r squared. Doesn't that make so much sense? Isn't that so much prettier than 2 pi r? That's my argument for tau.
I think this is the funniest argument because it's so stupid. Because
it's not stupid.
You're talking about using another variable on top of this beautiful variable that we already have. Now, here's my argument to that.
Because it makes the distinction.
Now,
it separates.
But it only distincts, like it is only be able distinct. It is only be able to distinguish between circles and between the circle circumference and the area. There are so many more uses of pi, and so many more times where pi appears in an equation, in a mathematical identity, a volume, 4 over 3 pi r cubed.
Use tau everywhere. I'm not saying you have to use it everywhere. I'm saying when kids learn about circumference, they think tau r and pi r squared. They separate the two, and then it's easier.
Now,
to me, it's easier.
Let me pose another point, and this is for for those people out there that understand a little calculus, because I do want to bring up a point that has something to do with derivatives. So a really nice thing about these circles and about all of these circular shapes, even in 3 dimensions, for example, is that their volumes, and when I say volumes, I mean volume in 3 dimensions, area in 2 dimensions, length in 1 dimension. Like, I mean, like the same, like it's based on the number of dimensions we're in. So when I say volume in 1 dimension, I'm talking about circumference of the circle. When I say volume in 2 dimensions, I'm talking about area of the circle. When I say volume in 3 dimensions, I'm talking about volume of a sphere, right? So a very interesting thing about these volumes is that they are all related to each other via the derivative. And I don't know if this is a coincidence. I don't know if it's a coincidence or it's just an interesting mathematical property, but the volume in 3 dimensions is what? 4 over 3 pi r cubed, right? That's, for those, like, might have memorized that formula. 4 over 3 pi r cubed. Take the derivative. We get 4 pi r squared.
With respect to r.
With respect to r, yeah, sorry. Take the derivative. There's no other variable. With respect to r, obviously. Take the derivative with respect to r, you get 4 pi r squared. Now that is the surface area of a circle. 4 pi r squared. Take the derivative of that. No, wait. It's pi r squared that you take the derivative of, that you get that. Sorry. Yeah, so your 4 pi r squared will translate your volume in 3 dimensions by taking that derivative. You understand the surface area of the same thing in 2 dimensions.
R cubed.
Sorry?
No, you said the 4 pi r squared is going to be the volume to surface area.
Yeah.
But it's 4 over 3 pi
r cubed.
R cubed.
Yeah.
That goes from volume to surface.
Yeah, that's what
area.
I said. Is that not what I said? Oh, sorry. No,
you said it the other way around.
That's what I meant. The 4 over 3 pi r cubed goes to the surface area 4 pi r squared. And that's just an interesting relationship between 3 and 2 dimensions. Let's talk about our circle's area and the circle's circumference. This is really cool. And this is why I condone the use of pi. And this is why I like the use of pi. Take pi r squared, the area of a circle. If we take the derivative of that, again, I don't know if this is a coincidence, but this would be really interesting to know. But if you take the derivative of that, you get 2 pi r, which is the circumference of a circle. So the perfect relationship between pi r squared, between the area of a circle and the circumference of a circle. So this is where tau would make no sense, because there's no tau anywhere. Like
but the problem is, I don't think people think about it.
Yeah, this is just my take on it, and this is just an interesting coincidence that I just wanted to bring up.
But if you do want to think about it, like why that does make sense, imagine a ball, right, with some radius, and as you increase the radius of that ball, the volume is going to increase. It just so happens that it's equal to the surface area, but you can imagine that it's proportional, at least, to the surface area, right? Because as you're increasing the radius, the amount of surface area around that ball is going to tell you kind of how much volume is going to be added when you increase the radius. I don't know if that was a little bit too hand wavy, but it's a way to think about it.
It was a little interesting for sure. So in this episode, we're talking, a lot about these trigonometric concepts, and we're also, introducing calculus now in some of it. So for those of you that have probably either not heard of trigonometry or want to know more about trigonometry, just learn it and, understand where we're coming from, you guys should check out brilliant.org. So Brilliant has some really cool courses on trigonometry. For example, they have some graph problem solving. They have inverse trigonometry, when we're talking about like inverse sine and cosine, and we're going to get to that. They also have some cool trigonometry graphs courses. And again, just a quick recap, Brilliant usually just has the one motto: practice, 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 where all their courses, they teach you the material, and then you're basically just, doing these quizzes. So it's a really nice way, to learn more.
As you guys know, you go on Brilliant, you learn, you practice. That's how you get good at, math and physics. So the first 200 of you guys to sign up with our link in the description, brilliant.org/MPP, will get 20% off your membership, premium membership. So go check that out.
Also, nowadays, we don't do it in the description anymore. I do it in the comment section because I don't know, just people can see it more, I guess. So yeah, sure. So description/comment section. Yeah.
So let's get to the meat of trigonometry, which is sine, cos, tan. And I know I mentioned this another time. The first time that I saw sine was actually in, I think it was grade 9 or grade 10 physics class, where we were learning about like reflection or refraction, something like that. And there's like an angle, like an incident angle that you need to calculate the sine of in order to get like the angle of the other beam. Anyways, the point is there's a sine of the angle in that formula, and I asked my teacher, what does that mean? And she just said, don't worry about it. And I'm like, okay, thank you very much. No. But it is very interesting when you actually do get to learn about what sine, cos, tan actually is, and why they're important, and where you can actually use these functions to solve actual problems. For example, when you get into calculus and you solve like optimization problems where it depends on angles and things like that. Now, to introduce this topic, or maybe just to go over it quickly, I guess we're not going to get like too deep into it, but imagine you have let's do the right angle triangle way. I guess that's the easiest way.
Okay. I think that is. Because that's the simplest way to explain sine, cosine, tangent. You're right. But like then moving from there, we can talk about some cool stuff. Yeah.
Definitely. So you have a right angle triangle. I always like to imagine the right angle is on the right, and then you have some angle on the left. And then you have your hypotenuse that goes across diagonally. And so the sine of the angle on the left side is going to be equal to opposite over hypotenuse. So it's just a ratio between the length of the side that is opposite to the angle divided by the length of the hypotenuse. That's literally it. Mm-hmm. And then cosine is adjacent over hypotenuse. Again, same thing. And then tan...
not same thing. I mean, it's a different, it's a different side.
Same thing, like different...
Yeah, I
like,
mean, it's dealing with the
idea.
adjacent side instead of the opposite. But yeah.
You just take the adjacent, for tan, you have opposite over adjacent. Again, opposite length of opposite side over length of adjacent side. And you can also think of it as sine over cosine.
That is how it's defined. Tan is defined as sine over cosine, which simply equals opposite over adjacent.
Mm-hmm. Because the hypotenuse cancels out when you do the ratio. So that's what they are. Why is it useful, Rehan? Maybe you want to touch on
why are sine, cosine, tangent useful? So, well, the first thing about these things is that, well, they are ratios, right? It's not a value that has, a unit to it. It's not that it has any meaning. It is simply a ratio between these two sides. And the advantage of that is that these ratios can be applied to anything. So if, let's say, I have a triangle that has a 30-degree angle and has some length, some side, and I just expand it to a really large level, but keep the angle the same, the ratio of everything stays the same. And that's the beauty of trigonometry as well. That no matter how big things are, as long as the proportionality of all of them remains the same, so like the angle stays the same, we have the same proportions. So basically we have the same ratios. So sine goes from from -1 to 1. So it simply has this, back and forth oscillation, and where we might get into, sine graphs and stuff like that. But before we touch into... do we want to touch into graphs right now?
No, I was just going to say the reason why it goes from -1 to 1. Yeah. And this is the visualization tool that everybody uses. So we have the unit circle. You draw a line from the origin to the side, or any point along that circle. And then what you do is you create a right angle triangle by, extending out from the origin along the x-axis, and then from the x-axis up to that point, you're going to get a right angle triangle. And now in this case, this is a unit circle. So the hypotenuse is 1. So sine of our angle actually just reduces to the opposite side, because it's opposite over hypotenuse, but it's opposite over 1. So the sine of the angle is just the length of the opposite side. Same thing for cosine. The cosine of the angle is just the length of the adjacent side. Now, you can... this is always so hard to do without actual visual aid.
Yeah.
But as you start from the x-axis and then you go counterclockwise around your circle, you can... I feel like this is so hopeless to describe with my words.
Let's try it. We can try it.
The cosine, right, the adjacent side is going to start at 1, go to 0, then -1, and then back to 0 and back to 1. And then the sine is going to start at 0, grow to 1, 0, -1, and then back to 0.
And again, all of that was simply the length of the opposite. Like if you simply think about it, right? Like when it's completely flat, the opposite doesn't exist, but the adjacent is 1, right? So like just think of that. Right. Yeah.
And the reason why this is like a cool thing, I guess, is because if you plot sine, like the the sine of and the angle versus the angle,
Mm-hmm.
right? You're going to get this wave pattern. And the same thing with the cosine. You're going to get a wave pattern that oscillates between 1 and 0.
No, 1 and -1.
And, 1 and -1.
Mhm.
And the reason why this is so useful is because now we can model things that oscillate.
Mm-hmm.
Like, for example, waves themselves,
Yep.
or springs,
Yep.
or maybe you're on a Ferris wheel and you can say, graph your height off of the ground. Well, if you're on a Ferris wheel, your height starts, at some point, and then it oscillates between the bottom of the Ferris wheel to the top of the Ferris wheel at a constant rate.
Something even simpler, you can just think about like a mass on a spring, right? Like if it's going up and down and up and down, it's basically oscillating. So there's some center.
Wait, sorry.
Yeah.
I misspoke. I said your height changes at a constant rate. I meant the wheel is spinning at a constant rate. The height doesn't change at anyways.
Oh, okay, yeah. But
Yeah.
anyway, so like as I was saying, you can just think about like a mass on a spring, for example, right? Like you have that equilibrium point, like at 0, and then it's kind of oscillating between going up and going down and going up and going down, and that motion can be represented as a sinusoid. Now,
Mm-hmm.
what is amazing about these sine graphs and the cosine graphs is if you plot them on the same axis, you'll see something where you can understand the relationship between both of these trigonometric functions. Man, my mic is falling. So the interesting thing about the sine and cosine is that cosine, if you look at the graph of it, it is almost identical in the pattern. It is identical to that of a sine graph, except it is shifted just a little bit. Now, why might that be? That's simply because of the inherent property of how we define sine and cosine. That at 0, at what am I trying to say?
The origin?
Not at the origin, but like at the
As an angle of 0?
Yeah, like the angle of 0, exactly. We have opposite equals 0 and adjacent equals 1. So we have sine equals 0, cosine equals 1. So basically the idea between sine and cosine is that they are complementary. So a sine of 35 degrees, or for example, the common example is sine 45 equals cosine 45, right? And then from there, like you can think about any other variation. For example, we have, sine of 40 will equal cosine of 50. So they are basically these complementary angles. That means if you add them up to 90, they will be the same. And the simple reason is because that is inherently how they are defined. When we have sine equals 0, cosine equals 1, and we start moving across the circle, you will literally see them just switch. They will be kind of going in a pattern where they're going towards the center, so they're oscillating towards the center, and they're going back and forth. They're meeting in the center, and they're simply going back and forth. So when this is 1, this is 0. When this is 0, this is 1. And that's simply the idea behind their oscillation. So even though their pattern is identical, it is simply shifted a little bit. And that is where we can use sines for everything.
One awesome thing about sine and cosine is that they are actually cyclical derivatives of each other, right? And not a lot of... Are there any other functions that have this property? I don't think so. Maybe like e to the x.
No, but not
it's
really e to the x is in its own category.
That doesn't count.
It's in its own category. No, I think this is the only one where explain.
What I mean by cyclical derivatives is that really quickly, if you take the derivative of sine, you get cosine, and then again you get minus sine, and then again you get minus cosine, and then again you get sine. Which means if you take 4 derivatives of sine, you come back to sine itself, which is kind of interesting because the rate of change, and you can, if you just plot this on Desmos or something, you can see that the rate of change of sine, well, mathematically it lines up with cosine, but if you graph it, you can actually see that, if you start at 0, the rate of change is exactly 1, meaning that you can plot the secant line is going to be exactly y equals x. Mm-hmm. And then as you move along sine, the rate of change equals out to 0 when sine of the angle is equal to 1, and then that is exactly when cosine is equal to 0. And you can do the same experiment with cosine and minus sine, and then all the other ones, because they all cycle back to each other.
And this is simply the beauty of sine and cosine. This is just the relationship between these two trigonometric identities, or trigonometric ratios. And they're beautiful because the advantage of this is that this can be used in so many applications, as we were talking about, in any scenario where there is any sort of oscillation. So you see this a lot in classical mechanics, like if you're ever dealing with, well, anything that's oscillating, like, a pendulum, for example. You can describe that using sinusoids. As I was talking about a mass on a spring, that's your common example. Or, famously speaking, quantum mechanics is also defined heavily via oscillations, right? There's some, without really getting too much into quantum mechanics, like there's some spatial inheritance of particles that oscillate, and they have positions that they can be in. There's certain probabilities of certain positions, and they're basically simply oscillations from different positions. So all of these can be represented via trigonometric sine and cosine.
Yeah, this is also related to quantum mechanics due to the wave nature of particles. Exactly. Where you have like a de Broglie wavelength.
That's kind of what I was saying. Like with the wave, like the spatial inheritance of the particle. Like that's kind of what I meant.
In this case, they're not oscillating, right? They just have a wavelength.
You can describe it via the oscillating wave, is what I was saying, right? Like
But the wave isn't oscillating.
True, but the sine wave yes, you're right. It came out in the wrong, like that's not kind of what I meant. I try to say that you can describe this wave-like property, this spatial inheritance of this particle via an oscillatory wave, which is sine. That's what I was trying to say.
Also, other examples where we do use trigonometry, for example, planetary motion, where you can have like angles in a period and all that stuff. That's not, it's true. What else was I gonna say? Not only triangles. It just so happens that triangles have a lot of interesting properties, I guess, with their angles. For example, the law of sines and the law of cosines, where the ratio between an angle and the opposite side is constant between all three angles and sides.
That's the sine law. That's the law of sine. Yeah.
And the law of cosine
is a little more complicated.
It's a little bit more complicated, but there's actually an easy way to derive it if you know a little bit about linear algebra. What you can do is you can draw a triangle with vectors. And then what you do is if you actually take the dot product with, what you do is you take the norm squared of you construct the third side of the triangle using the first two sides, which you can do with vector subtraction. And then what you do is you take the norm of that, and then you end up getting a dot product, which is where the cosine comes from. Because if you look at the law of cosines, there's going to be like some square terms and then a cosine. It looks kind of random, but that actually comes from taking the square of a norm where you get anyways. Yeah. It's
laws.
Cool.
Two cool laws.
It's cool if you do it.
And now I think we can safely talk about and even more, like there are just so many properties. There's just so many times when you're like trigonometry is cool. And that is when we talk about projections. So in the nature of projections, now when I say projections, let's just stick with 2 dimensions here. Like we can maybe translate it later. But let's say we have any vector, so like from the origin to some point on the xy plane. Now, an inherent property of all these vectors is that they have some coordinate in the x and some coordinate in the y. And these are very useful. For example, if we want to find the angle of the vector, we simply take a ratio of these two coordinates and we take the inverse tangent of it. Just a button on your calculator, if you may. So the idea, and maybe we can talk about that too, but like first I kind of want to just go through a little bit of projections, because we haven't really spoken much about tan, kind of left that guy alone. But it is useful. But with projections, the idea is that, let's say we have, as I said, some vector that's pointing to some xy coordinate. The point is, well, what do we do if we want to find the x coordinate of that vector? What do we do if we want to find the y coordinate of that vector? Like, how do we isolate both of those quantities, right? And where is this useful, you might ask? Well, think about
literally everywhere.
Well, literally everywhere for sure. But like, I'm just think about some object, like a force body diagram, if any of you guys remember that from high school, or if you just think of any object, let's say you're pushing an object. How do you find the net force? If you calculate all the vectors and all that stuff, like that's just a little too confusing. To dumb it down, you can just calculate the net force in the x direction, net force in the y direction. This is a really useful thing, and a lot of people who've completed grade 11 and 12 physics might know this. So how do you do this? Well, that is via projections. How do you find these components? Is via taking the sine and cosine of the angles that these vectors are on the Cartesian plane. Right.
And really quickly, the actual definition
Let's hear it.
of projection is, so you have like a vector and then you have a subspace, essentially. It could be a line, it could be a plane, for example. Let's just stick to 2 dimensions. We have like a line that passes through the origin, and we have some vector, and we want to know the projection of that vector onto that line. Well, the projection by definition is a vector along that line that is the closest to the tip of our vector. And so you can actually solve this analytically, which what you do is you actually model a function. So you have your vector that you want to find the projection of, which is just a fixed vector. And then what you do is you fix another vector that is lying on your line. And then what you do is you make a function that determines the distance between the 2 vectors, and then you minimize that function with derivatives, and then you can find the projection.
Very complicated.
Or if you want to do it geometrically, what you can actually do is you can draw a perpendicular line that, well, so you have your line and your vector. What you do is you draw a line that is perpendicular to your original line, and that meets up with the tip of your vector. And that intersection between your line and the perpendicular line will give you the projection of your vector onto that line. Now let's make it a little bit easier. Let's say our line is the x-axis, okay? It just so happens that this is really easy to do, to find the projection of a vector onto the x-axis, because if you have a vector, the closest point to the x-axis is just going to be the vector with just the x coordinates of your original vector, right? Also, this makes a lot of sense because that's how you find coordinates of a vector. You look like perpendicularly above the x-axis and you will meet up with your vector. Same thing with the y-axis. You go perpendicularly from your y component and you will end up meeting with the tip of your vector. And so once again, as we talked about earlier, you have a vector that starts from the origin and goes to some point. What you do is you draw that line that goes from the tip of your vector down to the x-axis, creating a right angle, and then you have your x-axis. That is a right angle triangle. So, taking the cosine of your vector, of the angle your vector makes with the x-axis, will give you, well, technically you have to multiply it by the length of your vector, but let's pretend it's a unit vector. You take the cosine of the angle, it will give you the length, its component in the x direction. Similarly, if you take the sine, it'll give you the length of the component that is in the y direction.
And a nicer way, and a nice way to think about projections, and I think this is also a way that they teach it, think of a shadow, right? The shadow method. And I think by definition, in linear algebra, when we learned the official definition of projections, it was defined as the shadow of a vector. In mathematical terms, it was defined as the shadow of a vector. So what does that mean? Is, well, again, let's say we have some vector. Again, hopefully you're just visualizing something originating from the origin, pointing to, I don't know, some XY point, doesn't matter. Think of a light shining down on the x-axis. What would you see? So that shadow is the projection in the x-axis. And if you were to now project it onto the y-axis, right? Like, I mean, if you're imagining the triangle in the first quadrant, like on the right, then your light is kind of facing left. So if you kind of project it on the y-axis, you get what? You get the y coordinate. So like thinking about it like in terms of shadows is kind of nice because because then you can apply that to higher dimensions. Because the moment you get to 3, you're like, well, how do I find the x and the y and the z? Because a projection in 3 dimensions, the 3-to-2 projection, is not x and y, right? It can be some combination of x and y. So a projection in 3 dimensions is, well, think of x, y, z. Now think of some random vector. Now remember the xy plane is just something flat. So think of a light being shone down, like shined?
I don't know.
Shone?
Shown?
Shone? No, not shone. Shined.
Shunned.
Okay. Shown.
Anyways.
Basically a light that is towards the xy plane. And that shadow, what you see, whatever combination of x and y you get, will be your projection. And obviously this applies to all higher dimensions too. Yeah.
You said that in 3 dimensions it's different, but it's actually not different because you can actually find, as I was talking about earlier, the projection of a vector in 2 dimensions onto a line.
Yeah, no, you can. You absolutely can. I'm saying on the xy plane.
I
was saying like if you're doing it on the xy plane, like something, something 3 dimensions to 2 dimensions, not 3 to 1. 3 to 1, you can just take the sine and stuff like that. You'll be fine with it. But 3 to 1, it's better if you think, 3 to 2, it's better if you think about it like a light shining on top because you can visualize what's happening there, you know?
Now, I want to say one last thing before we actually end the podcast here. This is really interesting. This is a big brain moment here, okay?
Let's hear it.
Now, we all know that we have like our vector spaces, but now let's think about function spaces, which can be defined. Yes, it's worth it. It's worth it. Here you go. I'm just going to go over it quickly. If you want to do more research on it, you can. But if you get it, it'll be very, very satisfying. So let's think about the function space of 2 pi periodic functions. Okay? Or, to make it easier, we can think about just like sine and cosine functions. Okay. And essentially, a vector in this function space is just a linear combination of different sine and cosine waves that have different amplitudes and different periods, right? Okay. So we did have an episode where we talked about Fourier Series, which is where you have any random 2 pi periodic piecewise continuous, this is just fancy for saying like somewhat normal function. Somewhat normal. You can write that function as an infinite sum of sine and cosine waves. Now, this is so satisfying because we just talked about projections, right? Now imagine this. You have, imagine in 3-dimensional space, you have a plane, right? A plane is some sample of vectors that is still like nice in quotation marks, meaning that if you have 2 vectors in that plane, you can still add them together and get another vector in that plane. You can scale any vector in that plane and it'll still be in that plane, right? But it's still just a sample of vectors in 3-dimensional space. Now, let's think about the function space of all continuous functions. As we know, sine and cosine waves are just a sample of the entire function space of continuous functions, okay? So you can think about the sine and cosine waves as this plane, in quotation marks, in the function space, right? Here's where it gets crazy. Actually, I take it back. I don't mean continuous functions. I mean 2 pi periodic functions, okay? So sine and cosine waves.
Okay. Yeah.
No, but listen.
Oh, yeah, no, continue.
So you have a function space. A function space is just, an element of this function space is a function that is 2 pi periodic.
Okay.
as we know, we don't just have sine and cosine waves, right? We can draw any function that repeats itself.
By the way, 2 pi periodic, because we haven't actually said that, is basically, as explained, just a quick thing. It's just that the fact that every 2 pi, it repeats itself. That's 2 pi periodic.
So anyways, here's where it gets super cool, okay? So you can imagine your sine and cosine function space as like a plane in this 2 pi periodic, piecewise continuous, just a little asterisk, function space. And the point of Fourier approximations is that you pick a vector in your 2 pi periodic function space, and the Fourier approximation is the projection of that function onto the sine and cosine plane.
Wait, really?
Right? It is. I read this in the text. I reread our notes and all that stuff, and they state this. It's insane, right? Because the more terms you add, the closer you can actually get to that function. But if you limit your terms, you have an approximation. You can think of it as you have like some restriction. You're restricted to a plane in 3 dimensions. But your function is somewhere else. It's not on that plane. But you want to get as close as you can to that function. So what you do is you take the shadow of that function onto the sine and cosine plane, and that point is your Fourier approximation.
What? Okay, that's pretty crazy, man. That's pretty
Isn't
crazy.
that crazy?
That's pretty crazy. I never knew this.
Yeah, I know.
I never knew this. That's pretty crazy.
Literally. Yeah, and the more terms you add, of course, if you go to infinity, the projection will be the function itself. But if you cut it off, then your approximation will be the projection onto the sine and cosine function.
Damn,
space.
that is a really cool property. Yeah. So like, I mean,
Yeah.
if you guys listen to our Fourier series episode, like that might make some sense. But if not, well, it really was a cool fact. That was a really cool fact.
Yeah.
Wow, I never even thought about it like that.
Yeah, and the way that like linear algebra, initially you learn about just vectors and stuff, but the minute you start thinking about function spaces and 2 pi periodic function spaces and all that stuff, like the possibilities are endless. You can do so many things.
Damn,
it's crazy. But yeah,
that's amazing. That's, I mean, truly the essence of trigonometry. You know what I mean? Truly, like this is crazy. This is so useful.
So,
what I noticed though is that we didn't even talk about like speed or angular velocity or anything.
Yeah, we can make an episode on classical mechanics. And
oh yeah, maybe we can talk about that stuff there, because even though speed and angular velocity do have attributes to trigonometry because it is based on that, it is more about, as you said, classical mechanics. It is about like how the object is actually moving, so it's a lot more to do with kinematics, dynamics, which, to be honest, just has trig in there. It's not really on trig. So yeah, so you're right. Maybe we can make a new one, make another one. So yeah. So
I hope you guys enjoyed this episode.
Absolutely.
Trigonometry. It was certainly fun to make.
Yeah, this was such a dope talk. Like, I really enjoyed it because, like, I found out that that's so cool, and the fact that was in our notes, so sad.
Yeah,
we didn't even see that.
I mean, this was at the very beginning of the year.
Okay.
Where like we had like they sent us like PDFs of the readings, and it was like super complicated. Like we were kind of learning about Fourier series, and we're like, we have no idea what's going on here. But I really took the time to read it, and when I read that part, I was like, this is absolutely mind-blowing, like very insane. Damn. Anyways,
that's pretty
thank you so much for listening to episode number 60 of the Math and Physics podcast. Make sure to follow us on Instagram at math.physics.podcast.
I just wanted to mention the 100K Q&A because, like, I don't know if people usually click away after we say this has been Math and Physics podcast. Like, I don't know our listeners out there, so let's just saying 100K Q&A. Just a quick reminder again for next Saturday. So if you guys can be on, like, that would be really cool. Where obviously it's gonna be only on YouTube, so it's not gonna be a Spotify thing or any. So any of you listeners, basically, like, if you guys like to listen to us, maybe you want to come see us. So yeah, just keep our Instagram posted. Just keep checking it, and we're just gonna update you guys there. So see you Saturday, hopefully. All right, that's it.
All right. So yeah, this has been episode number 60, Math and Physics Podcast. I am your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.